Good afternoon and good morning to all our participants in the US and in Europe. My name is Loïc and I'm the co-founder and CTO at Atinary Technologies. I am thrilled to welcome you all to our webinar today. Today, we all have an exciting topic, the revolutionary realm of catalysis optimization. We'll explore how the integration of artificial intelligence and robotics has transformed this field, enabling the efficient screening of vast chemical spaces, accelerating the discovery process, and enhancing experimental data reproducibility. I'm honored to introduce today's guest, our esteemed partner, Dr. Paco Laveille. Paco is the managing director of the ETH Zurich Catalysis Hub, SwissCat Plus. Paco holds a PhD in material chemistry from the University of Montpellier in France. He has an extensive background in catalyst technology and sustainable fuels production. He worked as a research engineer at prestigious institutions such as the Catalysis Center at KAUST and at ADNOC, one of the largest oil companies worldwide. Today, Paco will share with us how combining AI, robotics, and data analytics through Atinary SD Labs allowed his team to drastically accelerate catalysis development. The focus of today is on development methods that accelerate the optimization of heterogeneous catalyst for CO2 to methanol conversion. The work he will present here was recently published in Chem Catalysis from Cell Press and made it to the cover page. Last but not least, I would like to draw your attention on the toolbar at the bottom of your screen. You will find a Q&A module to type in your questions. We will monitor the chat throughout the presentation, and we will direct your questions to Paco at the end of the talk. Without any further ado, Paco, the floor is all yours.
Good afternoon, everyone. Thank you, Loïc, for the introduction and for inviting me today. I'm glad to present what we've been doing together recently, combining Atinary AI software SD Labs with SwissCat Plus automated and high throughput experimentation tools. So I will start with a brief intro about catalysis, throughput, and chemical space. Then I will present the SwissCat Plus capabilities in terms of hardware, data, and machine learning strategy. And I will spend a bit more time on our case study, which is related to the optimization of CO2 to methanol catalyst. So why do we need to accelerate catalyst discovery and optimization? You basically probably know that catalysts are compounds, organic, inorganic, or biological, that accelerate reaction rates. They basically reduce the energy needed to break and make chemical bonds. And as such, they are essential in our society. They are present in most of the industrial processes to producing fuels, plastic, food, and fine chemicals. So far, catalysts have been mostly designed to convert fossil feedstocks such as petroleum and its derivatives. But if we want to transition to a more sustainable chemical industry, we need new catalysts able to convert molecules derived from sustainable feedstocks such as biomass or greenhouse gases such as CO2. And obviously, if we don't want to deal with the global warming impact, we want this to happen quickly, not in another century. The point is that currently most of the conventional catalyst discovery process are pretty slow. It follows the typical iterative trial and error process where scientists, when they face a new chemical challenges, have to read tens of scientific papers to generate an experimental idea. Then they go to the lab, they synthesize, characterize, and test their catalyst, most of the time one experiment at a time, changing one parameter at a time. And then, except if you're extremely lucky, you need further optimization. So you go back, read more papers, combine with your experimental data that you have just generated, and go for another round of experiment. Depending on the chemistry, this cycle can take 1 week to 1 month, and sometimes more. So it means about 10 to 50 catalysts prepared and evaluated per year. But if you look at the typical experimental space studied when you develop a catalyst, you have a lot of variables to evaluate, such as the composition of your catalyst, which can be active elements, ligands, supports, or the experimental conditions, such as the solvent, the pH, the temperature, the concentrations. And if you go through all the possibilities, you easily reach hundreds of thousands or millions of combinations. So if you compare these two numbers, the throughput of a conventional lab with the typical numbers of possibilities in a chemical space, you understand that it can take ages before you find the right balance of the different variables. Luckily, most of the multidimensional space have multiple optimum regions, like the light colors represented on the scheme of the 8-dimensional space. And thanks to the hundreds of scientific papers you have read, you're probably navigating close to one of the suboptimal regions. But how far are you from the best performing region of your chemical space? And what would it take you to move away from a low performing region that you are exploring since months or even years? So that's why the SwissCat Plus and other similar initiatives have been created. We believe that machine learning combined with robotics and high throughput experimentation can accelerate significantly the development of catalysts in the coming years. So by implementing a rational statistical design of experiments supported by machine learning algorithm, you can reduce drastically the number of experiments needed to screen very large parameter space. Automation and robotic, of course, increase the accuracy of your experiment, removing all the human interference and operate 24/7. And high throughput technology, instead of generating one data set per loop, you generate tens or hundreds of data sets, accelerating even further the exploration of your chemical space. Of course, if you have such data generation, you need to have a solid data management strategy to facilitate the data processing, but also to facilitate the downstream application of machine learning. So the SwissCat Plus is a national Swiss initiative co-headed by ETH Zurich and EPFL. We receive a substantial starting fund from the government to set up 2 hubs, one in Zurich focusing on heterogeneous catalysis and one in EPFL led by my colleague Dr. Pascal Mieville, focusing more on homogeneous catalysis. So we are not a research group per se, we are a technology platform offering services and expertise to all academic and private research groups who can need it. So the SwissCat Plus East in ETH Zurich is hosted by the Department of Chemical and Biological Engineering on the Angerberg campus. We had 2 main phases of development. We first set the first lab, which is fully operational since January 2023, and we are now finalizing the preparation of 2 additional labs, which should be up and running this summer. As I said, we focused on the development of heterogeneous catalysts for the production of sustainable fuels and chemicals, but not only. As long as the chemistry can be handled by the tools, we are happy to support. I should also mention that we are not a full self-driving lab. We operate with islands of automated experimentation and manual transfer of the sample between the equipments, and we track every activity using barcodes. Why? Because our chemistry is very specific. We have specific activities, and the transfer of the sample from one machine to the other is not a limiting step for us. But we are working currently on filling those automation gaps. So quickly, for us, it's important to have a broad range of tools to support the different requests of our users. So in terms of synthesis equipment, we have a ChemSpeed unit, which we use for non-air sensitive chemistry. You probably know those machines. They can dispense liquids, solids fully automatically. They can steer, heat, cool, adjust the pH. In our case, it's combined with a centrifuge and a robotic arm, so we can separate the liquid and the solid phase, recover our solid catalyst and wash it, for example. Typically for solid catalyst, you have a thermal treatment. For these steps, we have a fully automated furnace, which can switch from vacuum to different atmosphere up to 1,100 degrees. We also have an Unchained Lab Junior unit connected to a plate hotel, which we use to store our catalyst library and dispense the right amount of catalyst for downstream activities. And we have recently installed a new Unchained Lab big Kauna unit inside the glove box, which is dedicated to air-sensitive chemistry. So it has roughly the same features as our ChemSpeed unit, but in a controlled atmosphere. So thanks to this broad range of equipment, we are able to synthesize very different type of catalysts, metal-supported, mixed oxide, zeolite, MOF, and so on. For testing capabilities, we have 24 fixed bed reactors from Aventium. It allows us to evaluate the performance of catalysts under gas vapor conditions up to 925 degree, 100 bar with different atmospheres. And 8 of those reactors are connected to a glove box, so we can evaluate also the performance of air-sensitive catalysts in fixed bed mode. We recently purchased a new ChemSpeed unit dedicated to batch screening. So it's equipped with 6 independent batch reactors, individual batch reactors, but also 2 microplate chambers. So those microplate chambers, we can evaluate up to 192 catalysts simultaneously with different atmosphere up to 100 bar, 250 degrees. Our big Kauna unit inside the glove box has also 8 individual reactors for evaluating the performance of air-sensitive catalysts in batch mode. And we also have a microplate chamber inside the glove box to evaluate up to 92 catalysts simultaneously. And thanks to those equipment, again, we can cover a broad range of catalyst applications, and I've named a few of them here, like CO2 hydrogenation, dry reforming of methane, propane dehydrogenations, olefin oligomerization, and so on. These are examples of chemistry we have performed recently. The last set of equipment is dedicated to catalyst and reaction characterization. We currently have a TGA-DS CMS to perform loss on ignition, temperature program reduction, and pulse chemisorption kind of characterization. We have different set of GCs to analyze the organic phase that we produce, an HPLC for aqueous phase, a GPC for polymer analysis. And we recently purchased a set of nitrogen physisorption equipment, a high throughput XRD and a high throughput ICP-MS. So as I said before, when you have such number of equipment generating a large number of data, you need to have a solid data management strategy. Otherwise, you start to end up with multiple copies of your Excel files or data files everywhere on the instrument, but also on the scientist computers, and everyone is processing the files as they want, and it's quickly get messy. So in our case, we want to have a data management strategy allowing us to automatically store and organize our data files, also automatically process the data files, and at the same time document the way we have processed those files. And it's also important for us to have a simple way to share raw and processed data with our users, but also with repositories to comply as much as possible with fair data principles and open research data initiatives. So how does it work? Briefly, so you have different instruments in the lab. Each of them generate raw data files. And the core of our data management strategy is an ELN, an electronic lab notebook, developed at ETH called OpenBees. And there's a lot of features we like on OpenBees. And the first one is a folder watcher. So basically, the ELN is connected to the different lab equipment. And as soon as a raw data file is generated, the ELN see it and automatically upload it to the right location inside the ELN. Basically, it analyzes the name of the file and organizes it in the right project location and experimental task. Then the next step, once we have performed all the experimental tasks with the different equipment and everything is uploaded inside the ELN, is to process the file. And for that, we have another Python script, which is going to automatically download each of the individual raw data file, clean them, process them as we want, make some calculation for conversion, selectivity, or whatever, and merge them through the barcode system into one unique process file containing all the experimental information. And this process file is uploaded back again to DLN fully automatically and organized in the right location. So once we have the process data file, then we can easily feed our machine learning software, and I'll get back to that just after. What we like also about OpenBees is the fact that we can easily share specific projects with our users, and it's also connected to repositories. So we can, once the data are published, we can easily send the raw, the process data, and all the script that we have used to process the raw data. On the other end, we use the NAS, where we have a copy of all our raw and process data to visualize the data. So we use different tools to visualize the data, such as Python dashboards or Google Looker Studio, to make quick visualization, quick plots, and share with our users to make decisions quickly on the data, and more advanced BI tools such as Tableau to prepare more polished plots for presentations or publications. So on the machine learning approach, you probably know that there are different ways of applying machine learning to chemistry topic. Most of the cases we see in the papers use very large data sets, either mined from published data on internet or generated by computational tools such as DFT, so simulated data. So though they are both valid and have been proven to be successful in different cases, they have some limitations, at least for us. If you mine data from published paper on internet, you may either collect garbage and then false your model, and also sometimes it's difficult to use data produced from different research groups using different equipment to generate an accurate model. On the other hand, simulated data are quite accurate, but sometimes far from the experimental world and difficult to reproduce. So we wanted to have a machine learning approach using experimental data only that we were generating inside our lab. And Bayesian optimization, you probably know, is one of the best tools for this approach. So I'm maybe not the best mathematicians or IT specialists to explain in detail what is Bayesian optimization, but I'm sure that Atinary's team will be happy to reply more technical questions at the end. But basically, for those who don't have the background, it's a data-driven probabilistic model, which is going to suggest experimental sample within the space that you define. And then it's going to feed a multivariate function over the data that you have produced, and analyzing the quality of the data compared to your study objective, but also the confidence that you have between your data points. And based on that, it's going to suggest a new set of experimental conditions trying to first explore the spaces of your chemical space where you have a high uncertainty, and also exploit the positive signals it has detected, which are close to the targeted objective. So basically, it rationalizes the screening of large chemical space, and it's very well suited for chemical studies where you have multi-constraint, multi-objectives optimization. And it reduces drastically the number of experiments that you need to explore the space. So if you know how to code, you can probably build your own Bayesian optimization. But being a technology platform, we wanted to have ready-to-use solution. And so far, there are not so many solutions on the market. And Atinary, SD Labs, we found that it was a robust and user-friendly, not requiring any coding skills. So it was perfect for us. It has been proven in different fields of chemistry, and for us it was the easy and quick solution to our machine learning application. So now let's have a look to our case study. So for this case study, we selected the hydrogenation of CO2 to methanol. So I don't need to explain the interest of this reaction, basically converting a greenhouse gases into a valuable compounds, which can be used as a fuel, an energy carrier, or to synthesize more complex chemicals afterward. And a class of catalysts used to convert CO2 to methanol are known as metal-supported catalysts. And as the name suggests, they are metal nanoparticles supported on metal oxide matrices. And based on the composition of your metal nanoparticles and your support, you can play on the rate of conversion of CO2, but also the selectivity towards different products. So there are tens and tens of elements which have been shown to be working for the conversion of CO2 to methanol, and the possibilities are almost infinite. But for this case study, we've limited our chemical space to 4 oxide supports: alumina, silica, titania, and zirconia, which are the most used at commercial scale, and 7 active elements: cerium, cobalt, copper, iron, indium, zinc, and potassium. We could have extended the chemical space, but for this case study, we wanted to evolve in a relatively small and known chemical space to evaluate how the Bayesian optimization would make decision and optimization. Then you have to define your constraint, your experimental constraints. In our case, we wanted the optimizer to select one support among the 4 and combine it with up to 4 active elements among the 7, but with total metal loading not exceeding 5 weight%. It doesn't seem like this, but if you go through all the different combinations possible with this constraint and chemical space, you reach more than 20 million possibilities. Then, of course, you have to define your study objective. In our case, we had 4 objectives: maximize CO2 conversion, maximize methanol selectivity, minimize methane selectivity, and minimize the metal cost, the cost of the catalyst. So once you have defined your chemical space, constraints, and objective, you basically have to set up the Bayesian optimizer to understand those parameters. So I'm not sure how the audience is familiar with SD Labs, but I put few screenshots just to illustrate how simple it is to set up such a study. So that's the homepage of SD Labs. You basically have to create a workstation, which is more or less a project. Then you put the different information related to your projects, the parameters, your variables, in our case, 6 elements for the nanoparticle, 4 oxide supports, the type of measurements you're going to make to evaluate the performance of your material. In our case, the conversion of CO2, the selectivity towards product A, methanol, the selectivity towards product B, methane, and the cost of metal. Then you enter your batch size, which is basically the number of experiments you want the optimizer to suggest per loop, per iteration. In our case, 24 sample per batch. The objective of your study, the one I just mentioned, and your constraints. So you have different ways of setting your constraints and objectives. You can, for instance, tell the optimizer to avoid exploring certain region of your chemical space where you know it doesn't make sense, or you can weight the different objective differently if one is more important than the other. And then once this is set, you basically run the optimizer, and it's going to generate an Excel file with all your sample conditions. So in our case, 24 sample. And the values that you see stands for the volumes of the metal salts we have to combine with the support to produce our different catalysts. So I'm going quickly, but you can really set the optimizer to fit your personal study and chemical space. And Atinary is usually very supportive in training the different users, also to help you set up those aspects. So once we have this Excel file, in our case, we basically upload it directly to our ChemSpeed station, and we start automatically to synthesize our 24 catalysts based on the suggested parameters of the Bayesian optimizer. We have a thermal treatment in our case, and then we evaluate the performance of the 24 catalysts using our fixed bed units. So we basically flow 30 bar of CO2 and hydrogen at 275 degrees, and we analyze the product coming out of each reactors. And then once everything is done, the data are uploaded in our ELN and processed automatically, as I mentioned before, and the results are sent back to the Bayesian optimizer, which analyzes the data and suggests a new set of 24 catalysts, trying to maximize the targeted objective. So in our case, this loop takes 5 days. The synthesis and testing of 24 catalysts. And we have repeated this loop 6 times, generating 144 catalysts roughly in a month. These are videos. I hope you can see them. Sometimes it's a bit slow, where you see the preparation of the combination of the different metal salts by the ChemSpeed unit, the dispensing of the solid support. In the middle, you see the first generation of 24 catalysts. The different colors stand for the different combination of metals. You see the barcode reading state, and on the last picture, a set of 16 fixed bed reactors from Aventium unit. Let's have a look to the result now quickly. On the top, you see the composition of the 24 first catalysts suggested by the Bayesian optimizer. The color stands for the different elements, potassium, cerium, cobalt, etc. And they are sorted by support, so alumina, silica, titania, and zirconia. So for the first generation, the Bayesian optimizer tries to explore the whole chemical space by performing a uniform sampling and basically try the different variables within the constraints that we have mentioned. So it tested the different support, the 4 different support, and combined it with up to 4 elements within the 5 weight% loading that we mentioned. On the bottom left, you see the performance of those individual 24 catalysts in terms of CO2 conversion on the y-axis and methanol formation on the x-axis. So the best performing catalyst will be on the top right corner. And as you can see, most of them have a poor activity. The right, we have computed the average performances for this generation in terms of CO2 orange, methane formation in blue, methanol formation in red, and the cost in green, blue-green. And you see, for instance, that this generation in average produces twice more methane than methanol, which is not exactly what you want, but that's the third generation. Only one catalyst was slightly behaving differently than the others and performing better, which is the number 17, and it's basically zirconia with 1.2 roughly weight% of zinc, 1.2 weight% of copper, and 0.5 weight% of indium. So then we fed back those data to the Bayesian optimizer, which suggests another 24 catalyst composition. And you see here the new compositions. And as you can see, the Bayesian optimizer has made a drastic move. It has identified immediately the combination of support and active phase, which is the most efficient, in our case, zirconia with copper. And that's the most well-known active phase for CO2 to methanol catalyst. And you see the drastic also improvement in terms of performances. On average, the CO2 conversion has been multiplied by 5. The methane selectivity, which is our side products that we don't want, divided by 4. The methanol selectivity multiplied by 10, and the cost divided by 4. And all of this simultaneously without any other inputs than the data generated on the first generation. So, of course, if you look at the compositions of those catalysts, you see that the copper and the zirconia were present on this best catalyst from the first generation, but you see that they are very different than this number 17. So the Bayesian optimizer really makes a deep analysis of the data, taking into account all the objectives and the constraints of your chemical space. And what we can see as well is that tiny amount of doping element can have a drastic impact on the performance of the catalyst. So this highlights the difficulty to optimize and to find the optimum composition for such catalyst. So then on the third generation, the Bayesian optimizer suggests to increase basically the amount of copper and doping element. Logically, probably it believes that if you increase the amount of metal loading, then you're going to increase your CO2 conversion and your methanol production. But actually, as you can see, it produces less performing catalyst. So we believe this is mostly due to an increase of the nanoparticle size. So at higher metal loading, you have more chance to form larger structures. And when you have larger nanoparticle, most of the atoms are trapped inside and not available for the catalysis. We can also see that the potassium doping was probably also not a good move. So then on the fourth generation, interestingly, the Bayesian optimizer has learned from this low-performing generation and suggests catalysts with a much lower metal loading, roughly below 3 weight%. And it manages to maintain and even produces better performing catalysts by doping the copper with mostly cerium and zinc, which are also the two main dopant known in this chemistry. And you see that for this generation, we gain an additional 10% in CO2 conversion. We divide the methane selectivity by 2, increase the methanol selectivity by 20% compared to our best generation, which was the number 2. Only the cost of catalyst has not been improved, but we are already quite low compared to the first generation. So we repeated the last time, so a 5th generation. And on this 5th generation, you see that the Bayesian optimizer is pushing further the doping of the copper with cerium and zinc. And basically, we gain a slight amount of performance, but it manages to reduce the cost by an additional 40%. But that's in average. In the 5th generation, we are not able to produce a better performing catalyst than the one we got on the 4th generation, which is this one. We get another catalyst with a slightly different composition, but the cost is a bit higher. So we stopped the optimization at this stage. For us, it was successful. We could show that the Bayesian optimizer was able to screen rapidly large chemical space, guiding towards composition of catalysts, which only a scientist with a deep knowledge of the field would have suggested, but it's not the case of the model. It doesn't have any knowledge of the chemistry. We could see that the model was learning from the low-performing generation very quickly and was doing this fine-tuning of catalyst composition, which is the difficult part in this chemistry. So we believe this really sets a new standard in exploring quickly and discovering catalyst composition. We could have selected a much larger space, but again, we wanted to observe how the Bayesian optimizer was behaving. But basically, it can be adapted to any type of chemistry, chemical space, and objectives. And currently, we are using this approach for many of our users with very promising results that should be published hopefully very soon. Another important features that we've noticed with the Bayesian optimization approach is that you can explore different regions of your chemical space by changing the objective of the model. So I'll give you quickly an example. This is the 1st generation that the Bayesian optimizer has suggested, which is a uniform sampling of our chemical space. When we have the minimizing cost of catalyst as part of our objective, it suggested this 2nd generation, mostly based on copper catalyst. But if you remove this cost minimization objective, then the optimizer, starting from the same data set, is going to suggest a totally different family of catalysts, this time focused on indium. So that's a very powerful feature, we believe, because you can explore different chemical space by changing your objectives. In this case, it was the cost, but you could target different product selectivity, different process conditions, for instance, etc. At the same time, it shows how sensitive the optimizer is to the objectives. If you don't set properly your objectives at the beginning of the study, then you may end up with an optimization which is not really perfect. It's I feel it's a bit like the prompt for ChatGPT. If you don't phrase properly your request, then you don't get a proper or the best answer that you can get. To put in perspective our study with the historical data or discovery made on CO2 to methanol catalyst, the first catalyst was developed in 1920 by BASF. It was a zinc oxide, chromium oxide. It took 20 years before we identified copper as a better active phase. It was supported on alumina. It took another 20 years to combine copper with zinc oxide still on alumina. Another 20 years to identify zirconia as a better support for copper catalyst. And then for a couple of years, the scientists have investigated the mechanism of this reaction. And only recently, some scientists have identified indium oxide as a promising active phase. So roughly in 6 weeks of experiment, we've been through 100 years of research related to CO2 to conversion to methanol, with basically the same milestone, but much faster. So as a conclusion, we saw that ETH has an operational state-of-the-art data-driven automated and high-throughput platform with broad capabilities in terms of catalyst synthesis, testing, and characterization. We are open to work with any academic and private research institutes, and we have validated the experimentally guided Bayesian optimization to screen very large parameter space using Atinary SD labs. And we believe this is a very efficient method, and it's going to set new standards to screen and accelerate catalyst R&D. And as an outlook, we are working on filling those automation gaps we have in the lab. Of course, we are exploring much larger parameter space, and we try to add more chemical knowledge in our machine learning approach, for instance, by inputting physicochemical properties of catalyst. And I want to thank the whole SwissCat Plus team who's doing an amazing work daily to support our different projects. And I thank you for your attention.
Thank you. Thank you very much, Paco, for this very inspiring talk and a great presentation. I suggest that we proceed now to the Q&A session. There are a few questions in the chat, and I'll start reading them out to you, Paco. So the first one that we have here is on the chemistry aspect, and the question is, what kind of data is collected during the experiments and how is it processed?
Okay. So we typically have CSV files, so Excel tables generated by the different equipment at this stage. So the synthesis tool generates a CSV with the experimental conditions, and the fixed bed testing, for instance, generate as well a CSV file, an Excel file, where we have the reactor process conditions, the temperature, the pressure, the gas flow associated with the different product detected at the outlet of the reactor, so the CO2, the methanol, the methane. And then we use, as I mentioned, we use a simple Python script a Python script that is going to clean, so remove data which are not useful. So sometimes, for instance, we test catalysts at different temperatures, but at the end we're going to keep only one temperature because that's the more relevant. So we remove those data on the process file and we combine with the synthesis data. So we have our composition of catalysts aligned with the performance, but that's mostly CSVs.
Thank you. Thank you very much, Paco. I have here another one on the automation part, which is what is the experimental bottleneck in bringing automation to chemical laboratories, and what steps still need to be taken manually?
So I think the bottlenecks depends strongly on the type of chemistry. I would say also the budget, because those tools are quite expensive. So obviously not every individual research labs can have a set of robotic synthesis tool and testing fixed bed units. They cost usually millions or above a million. And that's why I think universities are implementing those kind of core labs or technological platform where the tools are shared between the different research groups. And you said the bottleneck for automations.
Yeah.
I mean, in our case, we have small activities which are difficult to automate. For instance, you saw the fixed bed reactors, they are 2 millimeter diameter, the opening, and we have to transfer the catalyst powders in a certain way. We have to make sure that everything goes inside the reactors. And those steps currently are not yet fully automated. We are working into automating them. But I would say it sometimes costs a lot of money for activities that a human can perform quite quickly.
Excellent. Thank you. The third question is around the algorithm itself. And the question is, how well does the Bayesian optimization algorithm deal with process variability or variability of the data due to factors not described by the independent variables?
So what I understand is if we get low quality data during our experiments or the Bayesian optimizer, I think it's a good question. Probably the Bayesian optimizer won't see that you have low quality data. So I think you still need to have scientists checking sometimes and see maybe if you have outliers within your data and make sure that they are not fed into the Bayesian optimization.
Okay, thank you. The third one relates to one of your slides where you show how the algorithm can switch from one path to another one. The question is the following. You mentioned adaptation of the objectives after first screening rounds. Can the Atinary platform support this adaptation of objectives, for example, by simulation or certain scenarios?
So I think maybe you can answer better than me, Loïc, but I guess the answer is yes. I think you can recreate workstation and reuse the data that you have generated on a different project within a new project with different objectives. And how the simulation is performed, I think, you always need to prepare the catalyst. So the Bayesian is going to suggest a set of catalysts based on what you request. But if you don't synthesize and evaluate the catalyst, I don't think the Bayesian will go further than that. I don't know if you want to add something, Loïc.
Yes. So indeed, you can have the data that comes from different campaigns, and then you can combine them into a subsequent campaign to leverage this information and to have the algorithm that adapts. And then if there are simulation, in the end, what we can also do with the platform is to upload the data from the simulation into the platform, leverage this information such that you can adapt the search based on modelization. The next question is on the DOE, so more traditional approach. It starts with congratulating you, Paco, on this nice example of AI and automation. And the question is, how does Bayesian optimization algorithm compares to standard DOE techniques?
Well, I think the difference is the number of experiments you need to reach the optimum of your potential objectives. With a DOE, the more variables or parameters you have to explore, the more sample you have to prepare, and that's usually not feasible. Well, maybe that's feasible for some pharmaceutical or organic approach where they can prepare thousands or hundreds of samples quickly. But in our case, for heterogeneous catalyst, we are limited most of the time by the testing capabilities. And when we have 24 fixed bed reactors, I can tell you that's already a lot to evaluate 24 catalysts at the same time. But if we would use DOE, then we would need to multiply this number by I don't know how much, but much more, and that's not feasible, at least in our field of chemistry.
In particular, when the search space combines also with categorical variables, which make it extremely difficult and challenging for DOE methods.
Yeah.
The next question is, how is the catalytic converter positioned in the small tubes? Have you already tried the transferability to pellets with the optimization?
So we have not tried the transferability to extrudates or pellets. We can do it. This specific study was more to showcase our capabilities. And currently, most of our users, they are interested in powder catalyst. But that's certainly something we should and we will look at, how the performance from the powder transfer to more commercial shape catalyst.
Thank you. The next question is, in this example, the question is the composition of the first generation that you've shown of the catalyst, is it totally random? If so, is there any way to use data to influence the composition of the first generation other than changing the target? For example, conversion, selectivity, etc.
So I guess you're probably best positioned to answer this question, Loïc. I think it's not a totally random.
So I can answer this one. Indeed, so the first generation was not totally random. There is a procedure within the algorithm to suggest the first batch, and as we go throughout this loop that Paco showed before, the algorithm start to learn and then suggest more informed experiment to perform. Now, to the second part of the question, of course, if there is prior data that is available from past experiments, these data can be uploaded to the platform directly and then can be transferred to the algorithm for pre-training before it starts. And this prior experiment can come from, as mentioned before, it can be simulation. It can come from a DOE, from a high throughput experimentation, from some tests that were performed on the bench. So this doesn't really matter. You can upload it and the algorithm can leverage this. And maybe, Paco, a last question here is, what are the practical steps to implement such a self-driving lab approach in a typical R&D lab?
So, I mean, in our case, so we want to have this automation and high throughput equipment. So, I mean, you can always try to build your own high throughput automated equipment yourself. Sometimes you don't need to spend hundreds or millions of dollars on such equipment. But then once you have the equipment, it's quite easy. I mean, there's nothing really difficult. I mean, in our case, we use Atinary SD Lab, which is ready to use, and it's quite easy to set up. So you could, either with a simple unit, if you don't need fixed bed testing, you can do everything with a ChemSpeed or an Unchained Lab unit. You could perform a closed loop experimentation with only one unit, depending on your chemistry. But if I'm not wrong, you could also utilize SD Labs if you perform manual experiment or one or two experiments at a time without expensive high throughput tools. So, I mean, in our case, the first steps were to design and purchase the equipment. Then you have the design of the lab, which has to fit all those tools. And then, of course, you have the installation, the validation of the tools, and then you start to perform. So it's well, it took us about 2 years to set up this lab. So it's
Yeah, indeed, there's the automation part, but then, of course, as you mentioned, it can be done step by step, starting with onboarding first the AI component, running the experiment manually, and then slowly ramping up on the automation side, start to connect those equipment into the platform to go from manual to fully autonomous experimentation. Excellent. Well, Paco, thank you. Thanks again for this very inspiring talk. As this webinar is reaching an end, I'd like to thank you all for your participation. And we hope to find you found this webinar very informative. And we can't wait to see you again at future events. Thank you very much. I wish you all a wonderful day. Bye-bye.
Bye, everyone.